It's really amazing. It tastes good. Oh, okay. So we're going to talk about temperature and how temperature affects reaction rates. We know that a higher temperature means our reactant particles are moving faster. They have a higher average speed, average, right? Because they all move at different speeds. But there's a higher average speed, which means if they're moving and they have a speed, they have more kinetic energy. And if they have more kinetic energy, then that means when the particles collide, more of them will actually have enough energy, activation energy, to start the bond breaking, bond making process. So that means more of the collisional events will be successful, and the overall rate then would increase. Successful collisions leads to products. So let's review from chapter 5, kinetic theory of gases, where we said, hey, number of particles, if you were to plot that versus their speeds, we know there's a whole distribution of speeds, and they're not all moving at the same speed, and that's proportional to kinetic energy. And so these lower speeds, we've got these higher speeds. I'm just looking at this graph, and then there's some sort of average. Well, the distribution changes when we change temperature. So this is pretty much a low temperature plot. This would be like a little bit higher, like a medium temperature plot. And then this would be really broad and spread out. This is what would happen at a high temperature if we collected the data. So temperature, what's it doing? It's shifting up the average speed, right? If the top here would be some most probable or average speed, as we increase temperature, the average speed is increasing. Not only that, but the distribution is broadening. So let's say the kinetic energy, maybe we measured the amount of energy needed to activate a reaction. And so we measured it, and it's right about here, this much energy. So let's just draw a line there. So at that point, we would look over here, all these particles at low temperature. It looks like we really don't have any of those particles with enough energy to activate the reaction. They're just not moving fast enough. They're too lazy at the low temperature. The medium temperature, it looks like, oh, we do have some particles right up here. Some of the fastest particles definitely are colliding with at least that energy and more, so that can lead, you can get a little bit of reaction at that temperature. At the higher temperature, oh, look, we have more particles that are going to collide and activate the reaction. So at the higher temperature, we're going to get a faster reaction with more of these successful collisions. That's what we're saying here. Okay, so let's quantify this. Let's quantify something about successful collisions. So we can do that by examining what's called the Boltzmann distribution. The Boltzmann distribution is going to tell us about the curvature here, and we're going to plug in and on the x-axis here a particular energy values to tell us about the number of particles that have at least that activation energy and higher. So the Boltzmann distribution is a function. It's an e to the x function, an exponential function with a negative exponent. So this is it. The Boltzmann distribution quantifies the number of successful collisions. It's saying, hey, this function, if you plug in some value for energy, a particular activation energy, into the function, this calculation will give you the fraction of particles with that activation. So we have negative activation energy over RT. T is the temperature because temperature matters. R is the gas constant. Now we know the gas constant over here in units of liter atmospheres per mole Kelvin. When we talk about energy, we have to convert liter atmospheres to joules. So this is the R value we would like to use in this Boltzmann equation. 8.314 joules per mole Kelvin. Okay, so that's the Boltzmann distribution. It quantifies successful collisions. So what do we do with that? Well, we want to study kinetics, and we want to relate temperature to the rate of a chemical reaction. So the Arrhenius equation is going to help us do that. Arrhenius, actually, they were friends, Boltzmann and Arrhenius. And the Arrhenius equation is going to relate temperature, get temperature into the equation to a rate constant, which is proportional to rate. So we're going to get those together. How do we do that? Let's see. We know that the rate of a reaction is proportional to a rate constant. I mean, that's a rate proportionality constant after all. We also know that the rate of a reaction is proportional to the number of successful collisions. Well, the Boltzmann distribution quantifies the number of successful collisions. So rate is proportional to this, e to the negative e sub a over RT. Okay, so if rate is proportional to k and rate is proportional to that, well, it looks like k is proportional to e to the negative e sub a over RT, right? So let's turn that into an equation. K is equal to some proportionality constant times this Boltzmann function. Let's name the proportionality constant capital A after Arrhenius. Isn't that nice? E to the negative e sub a over RT. So this is called the Arrhenius equation. He named it after himself. So A is the Arrhenius factor. Now, usually we see the Arrhenius equation in a different form. Instead of the exponential form, we see it in the inverse. We see it in the natural log form. So let's take the natural log of both sides of this equation. The natural log of K is equal to the natural log of A times e to the negative e sub a over RT. Well, this is the natural log of a product of two things, so we could say that's equal to the sum of the natural log of each. Well, why do that? Well, the natural log of e to the x, that just cancels the operations. So e to the stuff, take the natural log of the result, it just cancels the operations. So we're going to be left with negative e sub a over RT added to this natural log of a is equal to natural log of k. That's the form of the Arrhenius equation that we usually see. So here's the exponential form. Here is the natural log form. So Arrhenius actually did this empirically, but Boltzmann is the one who actually derived it. It should be called the Boltzmann equation, but other things are named after Boltzmann, so he was okay with that. And what does it do? Well, it does what we wanted it to. It relates temperature to rate constant, which is related to rate. Temperature, we got it in the equation to rate constant and rate. And interestingly enough, this thing is in the form of a straight line, y equals mx plus b. We love straight lines. How so? The y value is the natural log of the rate constant. Let's see, the x, that's temperature. We'd like to vary temperature, so 1 over temperature is the x value, and everything multiplied by it is the slope. And then this natural log of k thing, natural log of a is this intercept. So that's just some number. So we have a form of equation of line. It's the same thing. I just moved those two terms, switched them. Wow, that means we could take data and plot our y value versus our x value. And it looks like we should get a negative slope. If we plot some data as natural log of k versus 1 over temperature, we'll get a data with a negative slope. We can fit a trend line to that. We can get a slope. Slope is negative e sub a over r. That's great. So I happen to have some data right here. This is something you'll do with your experiment from your lab project. You'll plot the data like this. I don't think you're going to have as many points, but you'll plot this data. You fit a trend line to it, and here's your equation of the line. The y value is natural log of k. The x value is all those 1 over temperatures, and that temperature is in Kelvin. And then you fit a line. Here's the slope, negative 22. Let's write that down. So we get negative, what can you see? 22,651 is our slope. And we set that equal to negative E sub A over R. What can we do with that? We could figure out what the activation energy is for this reaction. All we've got to do is multiply by this R value and the negative. So when we do that, we solve for activation energy, and we get 188,000 joules per mole. And that's so big, might as well express it as kilojoules per mole. 188 kilojoules per mole. So for our example, that's the activation energy of the reaction from that data. And so what does that mean? Well, it means that this reaction is probably pretty slow under room conditions because that activation energy is higher than 100. Right? That's the rule of thumb. Higher than 100. It's going to be slow. Let's do another example. Let's say we have a reaction that happens, pretty easily at room temperature. It only has an activation energy of 50. So 50 kilojoules per mole. Let's figure out what happens to the rate of the reaction when the temperature is increased from room temperature to body temperature. Okay, so if I'm going to increase the rate of the reaction, I've got two temperatures here, two temperatures. So what happens to rate? I got an activation energy, two temperatures. It's like I want to use this Arrhenius equation, and I want to use it twice. I got two temperatures, so it's like I have a T2 and a T1. And so the rate's going to be different, so therefore the rate constant will be different. That's a T2, that's a K1 and a K2 and a K1. This rate constant's happening at that temperature. This rate constant's different. It's happening at this temperature. The Arrhenius equation shows us that rate constant varies with temperature. Okay, so what happens to the rate? I've got my two temperatures. I guess I want to know the relationship between these rate constants. So let's combine the two equations. We do that a lot. In this case, I'm going to take my equation here and subtract the other equation. Subtract the two equations. So if I do that, the left side is going to be the natural log of K2 minus the natural log of K1. Then the right side, I got negative E sub A over RT2. And then I want to subtract this one. That's going to be plus E sub A over RT1. And then I got natural log of A minus natural log of A. Oh, that cancels. That's why I'm subtracting them. Get rid of the A thing because I don't know what it is. So let's clean up this equation just a little bit. I got a difference of two natural logs. That's the same thing as the natural log of K2 over K1. We know that log relationship. You can look that up on the handout. And then on this side, I'll clean it up by factoring out E sub A over R because it's common to both terms. And then I've got a 1 over T1 minus 1 over T2. So this is called the two-point form of the Arrhenius equation. Instead of graphing, I can put two temperatures, two rate constants for a given activation energy. This should look familiar. I actually did a very similar process here to get a similar two-point equation last semester. Yet back in chapter 9, Clausius-Clapeyron equation, you guessed it. We had pressures here, temperatures, and the energy here, instead of activation energy, it was a delta H of vaporization. Crazy. Yeah, it's pretty common to get a two-point form like this. So let's put our numbers in. So natural log of the K2 over K1, I don't have any numbers to put in there, is equal to it. Activation energy. Now, it's in kilojoules, but the R factor is going to be in joules. So I need consistent units. So I'll put activation energy as joules instead of kilojoules. And my R, 8.314 joules per mole per Kelvin. So joules per mole will cancel, and so will my kelvins. 1 over T1. My T1 is 25, but I need it in Kelvin. See, the units are Kelvin. So I've got to put 298, put 15 Kelvin, minus 1 over T2, 37, which is 310.15 Kelvin. All right. So the entire right side here, if you try this in your calculator, the entire right side is 0.78. So I've got the natural log of K2 over K1 is equal to 0.78. I want to solve for these. I got to get rid of that natural log. So I'm going to take e to the x of both sides. So e to the natural log of K2 over K1 is just K2 over K1. And then I got to do it to the other side, e to the 0.78. E to the 0.78, your calculator, try it. It's 2.2. So we say K2 then is equal to 2.2 times K1. That's about all we can do. So what does that say? It says what happens to the rate? Here it is. The rate constant at the second temperature, the higher temperature, is a little more than double the K1, the rate constant at the lower temperature. So if the rate constant doubles, then that means the rate doubles because rate is proportional to rate constant. So rate is 2.2 times the rate. So rate at higher temperature is 2.2 times the rate at the lower temperature. So what happens to the rate? It increases by a factor of 2.2. Very interesting. So variations on this example. For this particular example, we had a value here for activation energy, and we had 2 temperatures. And what did we do? We compared rate constants right there. Variations, we could be given different things. We might have to use this 2-point form of the Arrhenius equation to calculate K at one temperature if we know something about the K at another temperature and if we know activation energy. What? First order half-life. What is that? What does that have to do with K? Ah, we know that one. A first order half-life is the natural log of 2 over K, rate constant. We solved for that. First order, if you have a first order reaction, you could, if you knew the half-life time, if you knew a time there, like if T sub 1/2 is equal to 15 seconds at a temperature of 298.15 Kelvin, you could solve for this K. In that case, this K comes out to be 0.046 per second. So that's a K at that temperature. You could find K at another temperature if you know the activation energy as well. That could be useful. There's another one. What about just using this equation to figure out an activation energy? If you can't do a full plot, if you only have 2 points, you could figure it out an activation energy if you knew the 2 Ks and the 2 temperatures. You could get the 2 Ks if you had a first order half-life at one temperature and a first order half-life at another temperature. If you got the 2 Ks, the 2 temperatures, solve for activation energy. That seems like a common question as well. So that's it on our temperature studies.